Let's jump into my presentation on offshore wind competitiveness. I will try to make it maybe a little bit quicker to make up a little bit of the lost time. I start with the motivation for our paper, and the motivation is probably clear. Increasing electricity generation from renewable energies is needed to reduce CO2 emissions. A vital but controversial question, and that shows more than 40 participants in this video conference here, is how competitive renewable energies actually are and how competitive they already are. And this is at the heart of this research. Many countries use auctions to determine financial support levels for not yet competitive renewable energies, often paying the distance to the wholesale prices. And one example, and that was our motivation, is the German offshore wind, where auctions were held in 2017 and 2018. And in both auctions, we saw winning projects bidding €0 per megawatt hour. That was at the time quite surprising. And the question was, and probably still is, does this imply that offshore wind is already competitive? And we started and did a conference paper on this, which analyzes the implications of a zero bid, and they depend on the auction design. So just having observed zero bids in 2 German auctions does not guarantee that offshore wind indeed is subsidy free. We analyzed this and found a few things. First of all, we have to say that German auctions for offshore wind are implemented as one-sided contracts for difference. So the revenue, which is actually received by investors, is the maximum of B and P, where B is the bid and P denotes revenues from wholesale electricity prices. So if the wholesale electricity price is above the bid, which is of course near guaranteed if the bid is zero, then the investor finances the bid with the revenues from the wholesale electricity market, just based on wholesale electricity prices. And so this is the second point here. Zero bid thus implies the wind farm will rely on revenues from wholesale electricity prices alone. So this would mean that indeed, yes, zero bid says it's competitive. However, Germany also has low penalties for non-compliance, which means that if you win the auction and essentially have the right to bid, but if you then do not bid, you have to pay a penalty or you lose an auction bid bond, but that bid bond is relatively low. We calculate and estimate it to be roughly 3% of total investment. So here in that paper, we said, well, this has some properties of an option to build. So investors win the auction with zero bids, and then they wait for a while before final investment decision. And if, for example, costs fall or wholesale prices gain, then they take the final investment decision and invest. And if that's not the case, they decide against investment, and all they essentially lose is the bid bond of 3%. Second aspect is auction design feature in Germany. Costs of grid connection are not paid by investors. So based on these results, we concluded it's not clear. It's certainly a good sign, but it's not clear. We cannot really say that offshore wind is already competitive. And you see here the source where we published this was a conference paper. And I presented that paper at a conference 2 years ago in 2018 in Poland. And there I got in contact with Malte Jansen from Imperial College. And we discussed whether we could do some joint research collaboration on this. And I still remember this very vividly. First of all, it was a pretty good discussion, but probably even more important, it was exactly the day when Germany lost 2-0 against South Korea in the 2018 World Cup. But anyhow, during that soccer match, essentially, the idea was born to do a research follow-up paper on this and to broaden the databases for the analysis. And thus to make competitiveness measurable along the process. So this is the second paper I'm going to talk about. And then for that, we looked at all offshore wind projects that were auctioned from 2005 to 2019 in all countries around the globe that held at least 2 auctions. And that were 43 wind farms from 17 auctions in 5 European countries with 20 gigawatts of total installed capacity. These 20 gigawatts, at that time we had 28 gigawatts total installed capacity for offshore wind on the global level. So we have more than 70% of global installed wind capacity included. Okay, so what we did for these 43 wind farms was to compute the raw bids, first of all. And you see that on the left. And if you look at that picture, I would say you don't see that much. You see different countries, you see different auction dates on the horizontal axis, you see different raw bids on the vertical axis, but the point is, we would argue it's really hard to compare the German €0 bids with other bids, even though, as you see on the left axis, we have at least already harmonized everything to euros in the first place, and even to euros 2019. But nonetheless, maybe we detect a falling trend. Definitely we detect a very huge variability in raw bids, but I would argue this is not enough to answer whether these bids are competitive or not. So we went on from there. And we developed a measure to compute competitiveness and to make the different auction designs comparable. And that is the harmonized expected revenue I will introduce at this point. And what we did for that, we analyzed the winning bids using a monthly cash flow analysis, harmonizing the most significant differences between offshore wind auctions and in particular, of course, between countries. So we harmonize whether it's a one-sided or a two-sided contract for difference. We harmonize for the accounting of indexation. Most auctions are nominal, some of them are real, so inflation adjustment has to happen. We harmonized support durations. Most auctions have durations, payment durations between 15 and 20 years. However, some countries even pay for fixed energy budgets in terawatt hours. So we harmonized that. We harmonized wholesale price revenues, including, that's very important, market value factors. So we did take into account that in different countries, offshore wind can be expected to earn different shares of the base price. That's the market value factor. We harmonized grid connection costs, land lease costs, and site development costs. And last but not least, the choice of market reference price used as the basis for comparison to the guaranteed price, whether it's hourly or daily or a monthly average. And then we define the discounted average revenue per megawatt hour of electricity generated over the lifetime of the project. And we refer to that as harmonized expected revenue. So we calculate, as this says, but just to repeat and be more clear on it because it's very important, the discounted average revenue per megawatt hour produced over the lifetime of the project. And that we say that's the harmonized expected revenue. So this does include the bids, but it also includes the golden end after the bid or the subsidy duration expires until the end of the technical lifetime of the project. So everything the power station or the wind farm will earn until the end of the technical lifetime is included here and referred to as harmonized expected revenue in euros per megawatt hour. And this harmonized expected revenue has two advantages. First, it can be compared to both wholesale prices or the costs of other technologies as a non-subsidized benchmark. So we could say that this harmonized expected revenue is the expected revenue for the wind farm, and thus, if bidders are rational and cannot earn huge margins, then that's similar to the levelized cost of electricity they expect to have for that project. And that, of course, we can compare to wholesale prices, I'll come back to that, or to the costs of other technologies to assess competitiveness. So here we have a measure which we can use to compare and assess competitiveness. And second, of course, this harmonization enables us to compare the projects from different backgrounds, from different countries. And thus we can broaden the foundation for any analysis. It's not just founded on 2 German auctions anymore. So if we assess competitiveness, it's now founded on these numerous European auctions. Of course, we would always like to have an even broader database, but it's as broad as it can get at this point. Okay, so we did that. And that looks like this. And I think it looks much better than the raw data. Usually I have an animation here, but with this tool, we just discuss PDFs. So I just have to walk you through it step by step. Each symbol here shows the planned start of operation date against the harmonized expected revenue on the vertical axis. The 2 log normal regression lines depict trends, the left one for all bids, and the recent pretty steep ones for all bids from 2015 onwards. And in the red circle, you see that wind farms due to be built after 2020 are converging towards a range of 50 to 70 euros per megawatt hour. So this is the expected revenues in real terms these projects expect to earn over their lifetime, and thus they must be able to finance the investment costs and all the other project costs based on these revenues. And thus the LCOEs must be below 50 to 70 euros for those projects. And especially all of you who are familiar with conventional power plants, 50 to 70 euros is what you reach for those in terms of LCOEs pretty quickly. Even with moderate prices, you're often in a range of 50 to 70 euros or even above that range. The last units which bid into these auctions, especially in projects from Denmark, UK, and Germany, have even fallen to below 50 to 55 euros per megawatt hour. And this suggests the costs of offshore wind are at the lower end of estimated levelized costs of electricity for fossil generators. And again, market value factors are included here. Okay, we can go down the second road to assess competitiveness. We can use the harmonized expected revenue and compare, as you see here in bold, to the expected revenue that would be achieved on the wholesale market alone, as if the wind farm was purely a merchant project and would sell each and every megawatt hour on the wholesale market. That, of course, can relatively straightforward be computed. And the difference between the harmonized expected revenue, including subsidies, and this expected revenue on the wholesale market, by definition not including any subsidies, allows us to derive the effective subsidy that is being paid to each farm. Difference between what they would earn on wholesale market alone and harmonized expected revenue, including subsidies, is an effective subsidy. And if that is zero, this effective subsidy, That implies that the harmonized expected revenue is equal to the expected wholesale market price. And that, of course, also implies the project is subsidy-free. This was an idea of our co-authors from the Imperial College London. They are doing this, they suggested it, and I found it quite elegant to assess what we are interested in here in this project. Okay, and if we show the results directly, well, we show results for two separate cases. On the left, we assume that grid connection costs are paid for by developers and thus are included in the bids. Grid connection costs for offshore wind paid by developers. On the right, panel B, we assume they are socialized. So the German case, grid connection is socialized, paid for by consumers in the end, and not by investors in the offshore wind. And of course, on the right, if part of the costs can be socialized, you see that projects look even more competitive than on the left in general. So all the dots on the right, when the investors do not have to pay for grid connection, are below the dots on the left where they have to pay for grid connection. We did that on purpose, just neutrally placing both next to each other, because it's a highly emotional question whether grid connection has to be paid for by projects or socialized and essentially paid for by consumers. And we did not want to kind of diminish the value of our paper by entering and taking position in this controversial discussion. We just provided both and tell readers, look, wherever you are on that discussion, either you look on the left or you look on the right. And of course, you can already see that regardless of whether you are on the left or on the right, the effective subsidy for newer projects, especially, is pretty low based on our assumptions here. That's what we say here. If grid connection costs are socialized, offshore wind subsidies have reached -12 euros per megawatt hour for the latest UK auction. And a large cluster of projects received an effective subsidy in the range of -10 to +20 euros per megawatt hour. This finding implies that several wind farms could expect to earn less money under the two-sided British CFD support scheme than under wholesale market terms alone. So they would essentially pay back money to society, at least to pay for grid access. And if we are on the right side, if grid connection costs are paid for by developers, then of course it's not that rosy yet. Then the lowest effective subsidy is at 2 euros per megawatt hour, assuming constant wholesale power prices. Even a slight growth in market prices, about 0.3% per year, means the cheapest wind farms are subsidy-free. Okay, then we did a significant part on the impact of wholesale electricity prices. Of course, this effective subsidy, as we compare it to wholesale electricity prices or the revenue achieved purely on wholesale electricity prices, the impact of wholesale electricity prices is significant. However, as many of you know, and EWI in particular is doing a great job on forecasting there, it's imminently hard to forecast wholesale electricity prices. And again, we did not want to really take a stand on that debate either. We just provided sensitivity analysis here. From -2.5% per year, so assuming the wholesale electricity price in the future will fall by 2.5% until it will rise by 2.5% per year. And then we compute how the picture would look like in that case. The two upper graphs show the average of bids. On the left, again, with grid connection costs paid for by developers, and on the right, with grid connection costs socialized. And here on the left, in each graph, you see a wholesale price decline of minus 2.5% per year, while on the right in each graph you see an increase of plus 2.5% a year, and then depicted in the lines you see differentiated by country the effective support for the average of all bids submitted in that country. So the upper green line, which represents Belgium, shows that the effective support or subsidy for Belgium is still significant, while the blue line for the UK shows that those wind farms there are increasingly competitive, especially if we assume significant increase in wholesale electricity prices. In the lower part, we look at the minimum bids, and we see that in several countries, minimum bids, even if we do not socialize grid connection costs, so if they're paid for by developers, and we are in the left lower graph, even there, if we just assume moderate future increases in wholesale prices, for example, for Great Britain or UK and the blue line below, then we see that effective subsidies is negative or become negative. In case you're wondering, on the dots on those lines, that's the historic average, what happened for the last 15 years. So the blue dot at roughly plus 0.8 implies that in the past 15 years, electricity wholesale prices rose in the UK by roughly 0.8% per year. And that would imply, if that trend would continue in the future, effective subsidies in the UK, even if wind farms have to pay for grid connection, we already see they are competitive. Okay, I try to save a little bit of time here and will not dive into the details on this, and directly focus on the key takeaways. There are three key takeaways. First, offshore wind is commercially competitive at good sites in mature markets. So it's not only the German €0 bids, implying if they are realized, these projects have to finance themselves purely based on wholesale market prices and are thus by definition subsidy-free. It's a broader foundation we enabled here. For example, there is projects in the Netherlands which also submitted 0 bids, and they already have taken the final investment decision. Final investment decision has happened. So the investors took the leap and decided, yes, we are going to build no matter what. Well, not quite no matter what, but you know, a final investment decision implies quite a lot. So they start spending serious money, and they did that roughly half a year ago. So they already have spent significant money by now, even though it was a €0 bid. So at good sites, obviously investors believe they can finance those projects based on wholesale market revenues alone. Second takeaway, once bids are harmonized over the variation in auction design, the expected revenue stream of wind farms are homogeneous across countries. So the general trend holds for several countries. This finding suggests that different auction designs were able to translate cost reductions into decreasing bids. We would like to look at the details here, but we can already conclude that results are somewhat robust to auction design. Key takeaway number 3, the initial spending made on support schemes has been successful in helping to create a relatively new low-cost and low-carbon industry. So I say at least some of this progress has come from subsidies and investing into the very expensive first megawatts here. It remains an open research question, how much? And whether the money was indeed well spent, that's still controversially disputed, but at least it probably helped. And this is further research. I would like to conclude with that. One further research is to broaden the perspective beyond Europe. And of course, we are already working on this. We now have an even larger group of authors from China and from the United States, completing the picture, getting more than those 70% of concluded wind farms, just to broaden the foundation for the analysis even further. Then I already said the other two things: analyze differences between auction designs. What's the impact of, for example, two-sided CFDs or one-sided CFD? Very interesting, controversial aspect computed in the current German debate. Most of you are probably aware of that. We can have the means and the data to maybe provide some more insight on that. And last but not least, analyze the cost reductions for renewable energies, which are indisputably there, and trying to assess the causes. So was it really the German Energiewende? Was it really the 20 billion euros German consumers spend every year on renewable subsidies, which made this development possible? Or is it more like researchers, like here in the call, in the end, helping to bring costs down? So this is still an open question. I would like to do more research on that. With that, thank you very much for bearing with me, being so patient, especially after these technical issues. Thanks for listening.